Apoptosis, the cellular self-destruct mechanism. Imagine a city where old buildings crumble on their own, making way for new ones. That's apoptosis in our bodies. It's a programmed cell death that keeps our cellular population in check. Without it, we'd be overrun by rogue cells. Apoptosis is like a cellular janitor, cleaning up the mess and maintaining order, but sometimes this janitor gets a little overzealous. It starts taking out perfectly good cells. That's when we run into problems. Excessive apoptosis can lead to neurodegenerative diseases, while too little can result in cancer. It's a delicate balance, like walking a tightrope while juggling flaming torches. Scientists have been studying apoptosis for decades. They've uncovered its secrets bit by bit. It's like peeling an onion, with each layer revealing new mysteries. And just when we think we've got it figured out, along comes a new player, hydrogen. Yes, the same element that makes up most of the universe might be the key to controlling apoptosis. It's like finding out that the answer to life, the universe and everything isn't 42, but H2. But before we dive into hydrogen's role, let's understand what makes a cell decide to pull its own plug. The four horsemen of cellular doom. When a cell decides it's time to go, it doesn't just vanish in a puff of smoke. There are four main signs that a cell is undergoing apoptosis. First up is cell shrinkage. It's like the cell is trying to make itself as small as possible before it goes. Maybe it's hoping we won't notice it's leaving. Next we have apoptotic body formation. The cell starts breaking itself into smaller pieces. These pieces are like little packages, neatly wrapped up for other cells to consume. It's the cell's way of recycling itself, making sure nothing goes to waste. Even in death, cells are environmentally conscious. Third on the list is karyorrhexis. That's a fancy word for when the cell's nucleus starts to break apart. The nucleus is like the cell's brain. So when it goes, there's no turning back. It's the point of no return in the cell's journey towards death. Last, but not least, we have chromatin condensation. The cell's DNA, usually spread out like spaghetti, starts to clump together. It's like the cell is packing up its genetic material, getting ready for its final journey. These four processes are the telltale signs that a cell has decided to call it quits. Signals that trigger cellular suicide. Cells don't just wake up one day and decide to die. They need a reason, a signal. These signals come in two flavors, intrinsic and extrinsic. Intrinsic signals are like the cell's inner voice, telling it it's time to go. These can be triggered by things like DNA damage or lack of growth factors. Extrinsic signals, on the other hand, come from outside the cell. They're like a knock on the door, telling the cell its time is up. These signals are usually proteins that bind to receptors on the cell's surface. It's like a molecular version of the Grim Reaper, tapping on the cell's shoulder. Both types of signals set off a cascade of events inside the cell. It's like a Rube Goldberg machine, where one event triggers another and another until the final result, cell death. This cascade involves a whole cast of protein characters, each playing its part in the cellular drama. Understanding these signals is crucial for medical research. If we can control these signals, we might be able to prevent unnecessary cell death in diseases like Alzheimer's. Or we could trigger apoptosis in cancer cells, effectively telling them to knock it off and die already. It's a delicate balance, but one that could revolutionize medicine. Section 4, protein players in the apoptosis game. In the cellular theater of apoptosis, proteins are the actors. Some play the role of executioners, while others are the protectors. Let's meet our cast. First up, we have the bad guys Bax and the Caspases. Bax is like a hitman, targeting the cell's power plant, so the mitochondria. When Bax strikes, it's usually game over for the cell. The Caspases, particularly Caspars 3, 8 and 12, are the cell's executioners. They're enzymes that chop up other proteins, breaking the cell down from the inside. It's like they're dismantling the cell piece by piece. When these guys show up, you know things are getting serious. On the other side, we have the good guys, BCL2 and BCL-cell. These proteins are like the cell's bodyguards. They work to keep Bax and its cronies in check. BCL2 and BCL-XL are constantly on the lookout, making sure the cell doesn't accidentally trigger its self-destruct sequence. The balance between these proteins determines whether a cell lives or dies. It's like a molecular tug-of-war with life and death on either side. Understanding how these proteins interact is key to controlling apoptosis.